let me introduce myself. I'm Jason Valerie. I'm part of the product management team for Microsoft's Azure Blob Storage. And with me I have Jagan Devaraju, who's one of our group engineering managers, also responsible for Azure Blob Storage. Today we're excited to share with everyone a little bit of what we've been up to with OpenAI over the last couple of years and how we've been able to support them in the build out of the supercomputers that they're using to train the frontier models that everyone here I'm sure is already enjoying in the form of ChatGPT and otherwise. They use our platform. All of the data that they store and all of the training jobs that run to build those models are powered by Blob Storage. And it's been an incredible journey to support a workload of that scale. And we're going to dive in and share a little bit of what that looks like. So from an agenda perspective, I will set some high-level context about the AI training data pipeline. We'll talk a little bit about what it means to scale one of these supercomputers to support that training pipeline, and then the associated data platform as well, which are some of the other dimensions around how they ingest all of the raw data and manage that data set. We'll leave some key takeaways behind. One of the important things I want to stress, though, is that while we're going to cover in detail what we do to support OpenAI from an infrastructure perspective, I don't want any takeaways here to be that this is the only way that OpenAI trains. I also want to make it clear that some of the dimensions of scale and capacity associated with what OpenAI does is a very closely held secret, because you can imagine there's a lot of industry interest in sort of the size and scale of some of these things. So I'm going to be very careful not to use anything other than orders of magnitude. But you can take these things to represent Microsoft's frontier efforts related to supercomputers. So let's talk a little bit about the AI training pipeline. So as you think about building one of these frontier models, it starts with the data. And that's true of any AI model you're building. You want the data that's coming in that's human generated, the curated content from the internet, the private data sets as appropriate, and even heading into a world where synthetic data becomes a part of these models. Now, these data sets might be images, text, videos. They come into the system and then they need to be processed. And so the processing of this is something that looks a little bit like the analytics jobs we've been dealing with on our platforms for a number of years. That goes through cleaning phases, creating aggregations, turning these into vectorized, and we'll talk a little bit about what that means in a later section, training data that gets piped into these supercomputers for the actual training process to run. And these training jobs can take months, many months long from start to finish once you start training one of these big foundational models. And along that journey, you're going to need to checkpoint, and you're going to continuously checkpoint the progress of that training run, and that's another use case for unstructured data storage. And then the final model deployment. And so when I look at this data pipeline, there's really 2 exabyte scale workloads, the raw training data and the checkpoints. And those are the 2 workloads that really pushed the dimensions of our platform and required us to think differently about how we deliver our capacity to meet the needs of these supercomputers. So we'll spend quite a bit of time talking about those 2 specific workloads. The AI supercomputers. We refer to them as the thundering herd, and they continuously grow. Over time, more and more GPUs are being brought into these supercomputers. And let's just give you sort of a logical view of what one of these things looks like. So this is a data center. Top down, actually it's a bunch of boxes, but think about it as a data center. And as Microsoft has been delivering Azure in our infrastructure for many years, a data center was a mix of resource types. It would have different type of disk storage racks, object storage racks. It'd have general purpose compute, specialized compute, different networking gear, all intermixed in the data center. And this would support thousands of customers' workloads. Enterprise customers, cloud native customers, and frankly, Microsoft itself ran in these data centers. But something happened. We had to start building single purpose facilities to deliver these kinds of scale that we're talking about. And so these supercomputers that are being built, they are there are 2 resource types that kind of go into it. GPU racks and blob storage racks, and some networking gear to connect them together. And not only do we have 1 data center full of GPUs and blob storage racks, but we start to have 2 data centers, 3 data centers, 4 data centers, N data centers. These things keep growing, right? And we have to connect all of this capacity, an unprecedented, like space race moonshot amount of capacity, logically together into one logical supercomputer and one logical storage namespace to deliver these kinds of training jobs. We have a capability at Microsoft called an RNG. It stands for Regional Network Gateway. And what this does is it allows us to glue these different data centers together into a single RDMA network. So any GPU rack and any storage rack can speak to another in that same topology over RDMA, low latency, high throughput. And so our challenge was, how do we take blob storage at this scale and present a single logical namespace of many exabytes? Let's talk a little bit about the first gnarly workload. So I talked a little bit about checkpointing. Checkpointing is through the model development. And again, like I said, these things can take months. You have to make sure you have the ability to roll back to a previous milestone in the training epoch. There's a bunch of reasons why this is important. As you're going through and training these models, you're going to have hardware failures. When we're talking about the numbers of GPUs in this scale, they're going to fail, and they're actually going to fail frequently. You might have many GPUs fail in a given day. And in order to recover from that, you have to roll back to the previously known good checkpoint. And checkpoints are a synchronous process. What that means is that the entire training job across all of those GPUs must pause, those GPUs go idle, the contents of the memory of those GPUs get dumped out, and then the training job can resume. And then it's our job in blob storage to catch all that data. And it's a lot. And as more capacity goes online, they get bigger. These checkpoints are a function of the model size, the number of GPUs, and the parameter count, which is sort of correlated back to the model's architecture. And that's really what drives all of this capacity. But the capacity is only one dimension of why that's challenging. The real big challenge is the write throughput. And what we end up implementing is a write back cache. And so these GPUs checkpoint to local, and then the job resumes, and then they start paging those blocks out to blob storage for the long-term retention of them and to be able to recover from these failures in the future. You also checkpoint for job switches. So they may be training one model on a given day, and then for whatever reason, they want to switch to train a different model on the supercomputer because of different milestones or different research priorities. And so when that happens, they will do what's called a cold start. And a cold start means that you don't have any of the checkpoint shards, because each GPU has a shard, and that's a file. They won't have any of those shards cached. And so that means they have to reread all of those checkpoint shards back into the GPUs. And so that cold start is the high watermark for read throughput. All of those GPUs suddenly reading back their checkpoints. In terms of latency and IOPS for these things, they're actually pretty inconsequential, because what we're talking about in these checkpoints are big, large sequential reads and big, large sequential writes. These are very large files. They're typically represented what's called a Python pickle file, which is a form of serialization. So the contents of that file are all those floating point numbers that are sitting in the GPU memory. They serialize that down to a file and write it down as a Python pickle. There's a need to make sure we're managing these things. You can imagine that you're checkpointing every 5 minutes, 10 minutes, 15 minutes. You're checkpointing fairly frequently so that when there is that hardware failure that you need to recover from, you haven't lost the opportunity of being able to train during that window. Just a few minutes can have millions and millions of dollars of impact to these systems given their costs. And so you want the most frequent checkpointing you can to ensure that you're getting the most out of these systems. And so those things start accumulating capacity over the time. One of the capabilities we have is a last access time and the last modified time on our objects. And so they build retention policies around these. We can see when was this checkpoint looked at most recently, is it valuable, and then they purge the ones that they don't need over time. So that's the checkpointing workload. And we had some problems in blob storage. We have an architecture and a platform that we first brought out to market way back in 2008. And when we first delivered blob storage, we didn't scale beyond the bounds of a single physical storage cluster. We deploy our storage clusters in typically 20 rack units, but this can vary. We can build bigger clusters, but we typically deploy in 20 racks. And in the contents of that 20 rack unit, you actually have 3 layers of our distributed system. You have a stateless front-end layer, and this is where all the requests land. You have a partition layer, which is the index or metadata. This tracks where all of the objects live, all of the metadata about those objects, and then our stream layer. And our stream layer is an append-only file system where all of the bytes live. And so all 3 of these layers sit within that 20 rack unit of deployment. And then the corresponding capabilities of a given storage account are tied back to the physical capabilities of that rack. So you have a finite amount of throughput, terabits per second, ingress egress. You have a finite amount of TPS or IOPS transactions. And you have a finite amount of petabytes on a rack basis. And so the only scale out, we had no scale out capability, we only had a scale up capability. So as new hardware generations came along, we could increase all of those dimensions in a defined ratio, but we couldn't scale out. And so in order to satisfy these really hyperscale workloads, it meant we needed to make some investments. Our common customers up until 2016, we were able to accommodate with this kind of workload, but this kind of deployment. But as soon as we started seeing these big analytics jobs, and then certainly when AI hit us, we weren't going to meet those scale dimensions with this kind of architecture. So we're announcing scaled accounts. Scaled accounts is a new technology that we've been implementing, and it's not really one single technology. It's a whole bunch of things that we've been doing over the last several years that enable us to break through all of those different dimensions and limitations. And so if you think about the front end layer, it's really the thing that allows us to, solving this at the front end layer is really the thing that allows us to scale out the throughput. Solving this scale out problem at the partition layer is really the thing that allows us to solve out the TPS and IOPS and break through those limits. And solving this at our stream layer, our capacity layer, allows us to scale this out at that layer. And so we had to make targeted investments at all three layers of the stack to get to the point where we can start logically gluing these 20 rack units of deployment into something that can deliver effectively horizontal scale out unlimited capacity to support these exabyte scale workloads. And so with that, I want to hand it to Jagan to kind of do a little bit more of a deep dive on some of the things we did on scaled accounts.
Thanks, Jason. So as Jason was explaining this, we wanted to kind of elastically and dynamically grow the clusters to meet the needs of these workloads. So in the next couple of slides, we will kind of look at how a typical read and write workflow works. And so in this case, when we bring a whole bunch of clusters together to form this logical group, which is very dynamic, the request lands in, is load balanced into one of those clusters. And the spread of this number of clusters can be very dynamically. In the moment's notice, in seconds, we can add or remove clusters. That gives us elasticity. And we can do this for any storage account in our fleet. So this lands on one of the front-end nodes, and the data is persisted. The front-end knows the authoritative cluster, which holds the index partition. It uses the low latency custom protocol on RDMA to update the authoritative index partition. And once that is done, it returns success to the client. And in this image, there are two, but this can be done across tens of clusters. We have done it on tens of clusters. There is no reason for us to believe that this won't work across hundreds of clusters. Same thing when you think about reads. The flow is very similar. In this case, we talk about 3 clusters. The request could land in any of these clusters. The front end knows where the authoritative partition server is. It routes it. This loose federation allows us to scale. The front end in any of these clusters does not need to know within that index cluster where exactly the partition is served. Each of these boxes are hundreds of servers, right? So now we are talking about a scale which is thousands of machines involved, and we don't want single points of failure. We don't want single contention anywhere in the system. And that is what is allowing us to enable OpenAI to keep pushing the limits as the requirements keep increasing. And the second point to note is that this is all in the logical layer. So underneath, we can support any type of redundancy. In Azure storage, we have locally redundant storage, where the replicas are within a zone, and we have also zonally redundant storage, where the replicas are across availability zones. Availability zones are in the same region, but they are physically separated. That gives you more resiliency. And this architecture also carries over to geographically redundant storage, or we call it geo-redundant storage. So this logical layer enables us to do this. We can also do this for different media types. We have premium blob storage, which is SSD-based. We have standard blob storage, which is hard disk-based. So that we building this at a higher layer enabled us to use this in various things and also give that elasticity across various offering types. The other thing to about this workloads is the security, right? Due to the private nature of, due to the requirements of this, people don't want to expose these model weights, these data sets to the internet. So one of the technologies that is available in Azure and in other cloud providers is this private link, private endpoint, wherein the bucket need not be exposed to the internet. The way it works is that we inject that endpoint only into the VNets that the customer has. This injection of endpoint has historically scale limits because you are only injecting one endpoint, and that was one of the challenges that we had to solve, as opposed to elsewhere where customers have to make choice between either they want scale or privacy or security. We wanted to make sure that these terabits of throughput is available on these private links. We had to do a whole bunch of work for these scaled accounts to program these private endpoints to be spread across n of these clusters and load balance on this private link. That enabled OpenAI and other AI teams to kind of do all this without exposing their model weights and their data sets to internet. And this is also used by a lot of our enterprise customers in analytics space. So this is a very, for most enterprises, they don't want to be in the news that their data is exposed to the internet on a misconfigured S3 bucket or Azure Blob Storage, right? So that is a must-have. So I'll hand it over to Jason.
Thanks, Jagan. Hello? Thanks, Jagan. So scaled accounts do a number of things for us. They allow us to hit orders of magnitude more capacity, throughput, and transactions per second to meet the needs of our hyperscale customers. And that allows us to horizontally scale across any number of clusters. And one of the key things to remember here is that not all of that capacity is coming on at the same time. So it allows us to dynamically horizontally scale over time as new capacity is added to these accounts. It eliminates the need for customers to shard their workloads or shard across storage accounts. And I should add, storage account is another name for a bucket. It's what we effectively call a bucket. And there's no change to our public pricing. We're not offering a new product or a SKU. These are foundational technologies into our service, which we're rolling out not just for the supercomputers, but all of our customers. And as a result of this, we're lifting the limits to all of our public customers to on average, 67% more than what they are today. So across our fleet, all of our customers are benefiting from the innovation we've put in to support these hyperscale workloads. Let's talk about the AI data platform. So, the actual training data that goes into these systems is the key special ingredient that makes these models work. And that's another exabyte scale problem of a different set of dimensions. So, customers like OpenAI are ingesting data from all kinds of sources. They have streams coming in from partner providers. There's web crawlers going out and indexing the internet. And all of these data streams are coming into the systems that need to be processed. And our system is the ingestion point for these things. And so in a traditional sort of space, you might choose to use something like a Kafka to take those incoming streams, store them for processing later. And we have some unique capabilities on our platform that we leverage to actually solve this same set of problems. When you think about this data that's coming in, again, I sort of mentioned it earlier, but this is things like text and images, videos, even Parquet files. And they're small in nature. They're kilobyte size or maybe megabyte size, but they're not gigabyte and terabyte size objects typically. And the growth here is based on the data acquisition that is happening. And so as you can imagine, there's a lot of data acquisition efforts going. And this is how we get to sort of those exabyte scale dimensions. The throughput here is really only during the ingestion phase. So these aren't actually super high throughput workloads. The read heavy during pre-training, but really where these things push our systems is more on the IOPS and latency. So they have the other dimension of requirements. During that ingestion phase, because these are lots of small files, there's lots of small HTTP requests coming over the wire, and those things start to pile up and be what drives those transactions. And then on the latency dimension, because these things are small and you're doing lots of iterative reads, lots of iterative writes, things like time to first byte latency actually impacts the processing. I should also note, this isn't happening on the GPUs. These are all CPU-based clusters. So there are big CPU-based clusters that are going out there for these sort of data processing workloads. And so we had to come up with some solutions to this problem as well. I'll start off with something that we have in our platform, and this is actually something we've had since day zero of blob storage. It's a fundamental difference in how we think about the block list compared to multi-part upload. So if you're familiar with other object storage platforms, there's this notion of multi-part upload that allows you to chunk an object and send it in multiple requests. We have a similar capability, but we call it a block and a block list. And we have this notion behind the scenes of something called an uncommitted block list. And so as you're ingesting a stream of data, the block list can send these blocks in a put block call. So you're calling put block against the name of the object you're trying to write with a block ID and the payload, the bytes for that block. Now, in the world where you're ingesting a bunch of these small files, you can write each one of these files as a block. And these blocks don't have to have the same length, which is a unique capability we have. And you don't need to know how many blocks you're going to have in advance. And so as you're uploading these blocks to the system, eventually you get to the point where you want to finalize it. And this is really bin packing. So if you've ever kind of thought about bin packing, it's this idea where you can combine lots of objects, lots of files into one larger file. This is a tar file, right? And so when you finalize this thing, you call an API called put block list, and then we create an object that contains all of that content in one big file. So now you can start doing big sequential I/O. We support up to 4 gigabytes per block and up to 50,000 blocks per object. And this allows us to do efficient continuation. If streams get interrupted, you can resume them. If you have multiple streams incoming, you can do parallel out-of-order writes and uploads. And ultimately, this creates these big bin-packed files that then can be fed into the analytics systems. And this, let me hand it back to Jagan to talk a little bit about some of the challenges we had around like the partition space to accomplish this as we start to hit those really high IOPS numbers.
Yeah. So when we talk about scaling, it's not enough to think of scaling in just dimensions of horizontal scale out, right? Most workloads cannot be successful if we give them a lot of IOPS, but they have to use the entire namespace and to use all that IOPS. We want to make sure for any practical things, all these IOPS could be used in a very small corner of the key space. Say for example, the data set, right? So somebody wants to create a data set with this month, then the entire pipeline will kind of converge on this dormant namespace, which never existed. Before, there was zero load because they are freshly created. And from that partition gets from 0 to hundreds of thousands of IOPS. The Azure Blob Storage, like almost all other object storage, is range partitioned. So based on prior load and heuristics, we range partition it. So what happens is this key space which had 0 traffic suddenly gets hundreds of thousands of IOPS. We did a lot of work to make this load balancing really fast so that within matter of seconds, we can spread this index or this partition split into multiple key ranges and be spread across a lot of servers. What enabled us was that we store the index data in the distributed file system as opposed to local. This is something we cover in the original object storage paper, in the original Azure storage paper. So that, along with all the optimizations we did to load balance in low single-digit seconds, enabled us to kind of deal with this thundering herd of CPUs coming in and uploading data into a namespace. It also helps when a thundering herd of CPUs come and start reading this index, because they might stop processing, say, the data set 1 and then start processing another data set which is all in a completely different same namespace. Same thing when a checkpoint might be organized as a new location in the namespace. That's the logical way to do. Whenever you have a new data, you create a folder and put it there. So that dynamism is what enables us. We can do thousands, even hundreds of thousands of load balancing operations in low single-digit seconds. And this is something, it's not purpose-built for OpenAI. We do that day in and day out for all customers using blob storage. Same point about capacity scaling, right? We talked about how we are distributing data over n clusters. That distribution that you had yesterday might not be good enough for tomorrow because more capacity might have landed. You want to level load the capacity. You don't want all the new capacity to be available in one corner. That means all the writes have to go there. And sometimes it makes sense, but other times you want to have the entire fleet take in all the writes. You also want to make sure that you want to decom some of the older hardware, and you also want to make sure that you want to load balance for reads. That's a learning that we had as we were building it. Initially, we thought about mostly balancing for capacity and for new capacity, but we started running into workloads that were keeping the spindle super busy because of the thundering herd of CPUs and GPUs. Then we started kind of thinking about how we need to load balance some of these hotter ones just to deliver more read throughput. What we built is a very fine-grained migration of small chunks of data. We can migrate even small at a gigabyte level for these exabyte scale workloads. We have the ability to do that seamlessly and in a completely scaled out fashion. We can go instruct a bunch of disk nodes to pull in data from the other disk nodes without needing the data to be moved into the higher layers and pushed down. That is another work that we have been doing over the years to enable this elasticity and capacity scaling. With that, I hand it over to Jason.
Okay, we need a client to connect all of this together. So you've got the GPUs and you've got all of this capacity that scaled accounts provide us, but what's the glue that binds these? I'll first say that OpenAI has a variety of different clients they use with a variety of different caching capabilities that I won't bring into the context of this talk. That's their intellectual property. But what we position for our other customers and how we see this kind of going for the common Azure customer is a capability we call Blob Views. Now, what is Blob Views? Blob Views runs on these GPU hosts, and it gets the opportunity to govern some local resources. So if you think about these training instances, Microsoft has our current generation of GPU compute is an instance type we call NDV5. An NDV5 training instance has 8 of the H100 GPUs attached to it. It has a big beefy Intel processor. I think it's a 96-core Intel processor. And it has 1.9 terabytes of CPU memory. This is in addition to the HBM memory that's on the GPUs. And it has 36 terabytes of local ephemeral NVMe. It's attached to the host, not durable in any way. And so we need to be able to do that write-back cache I talked about earlier to support the checkpointing, and that has to go somewhere. And so what Blob Views does is it presents to the customer or the user a file system mount that then can leverage this RAM and this NVMe for caching. It can use the RAM for the write-back cache. We can store data onto that local NVMe, and we can use this to normalize all of the throughput back to the scaled account. And then that scaled account is backed by many different storage clusters. And so, when you think about this, you're not, the folks that are using these systems are not developers. They're data scientists, they're AI training experts, but they don't want to use SDKs. They don't want to have to think about object storage. They come from a world like most of us where they use file folder semantics to organize their data. That data set just has to be exabyte in scale. And so how do you take this exabyte scale world and bring that into something you can manage from a file folder hierarchy? That's where Blob Views comes in. The corresponding capability that we have is something we refer to as the hierarchical namespace. And this is an index layer that sits over top that core partition that Jagan was talking about that allows us to do operations on a file folder hierarchy. And so you get this ability to do things like rename files, atomic delete of thousands and thousands of files in a given folder, all from a Linux command line. And this can happen at the exabyte scale. Again, caching is an important piece to provide the performance our customers expect. Today, we have the ability to use that local NVMe and that local memory to do block caching. So we can write to that cache and then read back our writes. And we're looking at investments into things like prefetching for Blob Views. So we can hint to the mount point that there are certain data sets that it should pre-stage on the local NVMe. And ultimately, one of the capabilities that OpenAI have, which we're looking to bring into Blob Views, is to be able to treat all of those GPU nodes as a distributed fabric cache. If you think about all of these GPU nodes, they have very high bandwidth interconnects, often over InfiniBand. And it would be really great to be able to do reads off of your peer node versus going back to what OpenAI refer to is our spinning pile of Rust. They lovingly refer to us as a spinning pile of Rust, but we're a hard drive-based SKU. And so all of this very high-performant NVMe is an opportunity to build a distributed cache in front of the hard drives to blend the best of performance and capacity. So that's Blob Views. And I just want to kind of give some benchmarks of what we can do with Blob Views today, right now. And so we did a quick test. We did 16,800 vCPUs pointed to a scaled account. And with that, we were able to do 8.1 terabits per second of ingress and 13.5 terabits per second of egress. Now, that's not cached. I want to be clear. This is actual throughput coming out of Blob Storage to Blob Views across all of these instances. What's that?
Drives.
No, this is coming out of the Blob service into Blob Views with no caching. That kind of number is only limited by, frankly, how many vCores we threw at the problem and how many racks of storage we had behind the scenes. And that just continues to scale out given this architecture. Now I want to talk about the global GPUs. So, these supercomputers are big, big, big monster deployments, but there's a space race on, and everyone is trying to deploy as many GPUs wherever they can, as fast as they can. And when you look at Microsoft, this is what a typical Azure region looks like. And we have, I think we're knocking on 70 Azure regions around the globe right now that look maybe something like this. When you start thinking about that global footprint, there's a lot of empty space and power we can go cram some GPUs and bring them online. And Microsoft's doing just that. And so there's a new problem that emerges, which is how do you move your data sets, those training data, the training data we talked about, as well as the important checkpoints back and forth from these big central storage sites. We've built out these multi-exabyte storage sites to support a customer like OpenAI, but they're now getting GPUs all over the globe. And so we have to leverage our WAN and some interesting storage capabilities to support that kind of data movement. This is clearly a marketing slide, but it's a fun one. Our WAN is huge. One of the things that Microsoft has really invested in over the years is providing networking capability for the globe and for all of our first-party services. So if you're having a Teams conversation with your colleague, that audio flow and that video flow is going over Microsoft's global WAN. If they're sitting in Europe and you're sitting here in California, you're taking our WAN to do that. And that WAN doesn't have 100% utilization all of the time, and it presents us an opportunity to more efficiently move our data around the globe. And so what we have is this brokered WAN capability that we've deeply partnered with our networking team to support in our storage platform. What the brokered WAN does is it takes all of those links and allows us to tag traffic as slightly lower priority and then aggregate a diverse set to be able to deliver the maximum throughput. So let me give you an example. Point A, let's say that's Azure Region A, and point E, let's say that's Azure Region E. Those are representative Azure regions around the globe. Maybe one's here in the US and one's in Europe. And you can imagine that the top T0 or priority 0 sort of path going from A to C and C to E, each of those are links that we observe 1 millisecond of latency, and in this case, I don't know what the unit of measure, we'll call it 10 gigabits per second, sort of irrelevant. And they're utilized at 100%, right? And they're carrying your team's voice traffic or whatever sort of Microsoft service or other customers in the Azure network are carrying that priority traffic. And so, trying to squeeze the bytes over that network flow would be constrained and limited. And so what the WAN enables us to do in this case is to use all of the paths coming out of region A and all of the paths coming out of region E to fill in the valleys, right? So as throughout the day, you've got these diurnal natures of network traffic, and in all of those valleys, we can fill them up and keep all of those links running at 100% saturation and aggregate it. And so you can imagine going from A to B to D to F to E, you can imagine going A to D to F to E, and you can take all of that aggregate throughput and use it to move data. Now the consequence is latency goes up, right? But we're talking about data movement, and so data movement isn't really constrained by latency. These are ad hoc data movement jobs to get ready for a big training run. We need to go push petabytes, hundreds of petabytes in some cases, from one place to the other, and we can fill those links up to do so. And we observe, depending on the origin and destination within the Azure region, many terabits of aggregate throughput of data movement around the globe. And so how do we do that from a storage lens? We have a couple of APIs in our platform which are actually unique in terms of the public cloud and the hyperscalers. They're cleverly named put blob from URL and put block from URL. Now earlier you saw put block, like we're putting blocks of data. And the expectation of the put block payload is that you're giving it the bytes in the request body, right? So you're putting the blocks. But put block from URL doesn't accept the bytes, it accepts the signed URL. So what happens is we have an orchestrator that knows the objects you intend to move. So maybe you've got 1 million objects you want to move from West US 3 to Sweden. So you've got this list of objects, you can go and sign the URLs. And so if you're familiar with object storage systems, this is a common capability that you can take the full path to the object and you can do a one-way signature using an HMAC 256 key and append that to the URL, and that becomes a fully signed URL, fully trusted URL. So you take all of these million objects and create 1 million signed URLs, and you high degrees of parallelism call to the destination. And so you're calling Sweden and saying, hey, I want to put block from URL, and the payload is the URL to the source back in West US 3. So all of our storage clusters in Sweden now open up concurrent HTTP requests across our WAN back to our facility in West US 3 and start reading the bytes directly across the WAN to Sweden. And then we hold that client orchestrator connection open. Once those bytes commit themselves back to Sweden, HTTP 200 OK, the client releases it, it acknowledges that we now have a consistent state between the two sites. So put block from URL, put blob from URL, our tier 2 WAN come together to allow us to do multi-terabit data flows between any 2 points in the Azure globe. So that's the set of capabilities we've been working on. I'll leave you with some key takeaways. The scaled counts capability is what's enabled us to fully horizontally scale our capacity out dynamically in response to growing needs over time to a single logical exabyte namespace. The Blob API and some of the unique characteristics it has around the block list enable us to do better stream-based uploading and bin packing. Our hierarchical namespace enables us to provide file and folder semantics at the exabyte scale to the data scientist persona. Blob Views exposes that to them. We have a dynamic partition splitting capability that allows us to drive the kinds of IOPS these data processing workloads need. And these data movement APIs and Microsoft's investment in its global WAN allows us to move data around the globe at terabits per second. So that is what we've done for OpenAI. Questions?
When you pack the blobs together, do you compress on that? Do we, at the storage level, expect that we're going to see large reads for that kind of interaction?
I mean, the rationale of bin packing is that when you're actually doing upstream processing, the question was, when we bin pack the files, do we expect there to be processing at the file level, I think is what you were getting at, or how does that play into the upstream?
Compressing, so then we'll see large reads to decompress. What can you do?
Yeah, so bytes typically, I mean, certainly if you're thinking about like images and videos, that's obviously compressed bytes already before we get it, so compression isn't super useful. The system compresses once it gets down to the stream layer. We don't compress on the fly, but the objects do get compressed before they get written at rest, is maybe the question. I don't know if you have additional?
I think based on size, we do kind of lay it out slightly differently. Sometimes when these blocks are larger, we might leave it at wherever they are. Sometimes we might decide that it makes a lot more sense to bring some of them smaller ones together. It is based on a bunch of heuristics, and some of it is something that will vary over time. So I understood as layout. He was understanding it slightly differently. I'm not sure which.
I think I get it.
Yeah.
Thanks.
So you talked about the checkpointing problem, right? I think you described what I understood as checkpointing moves to a nearby storage before it all gets lazily written down to block. Right? So my question is, when checkpointing is more and more becoming a problem, is it a problem for the drives or whatever the storage media, or is it a networking problem, or both? How have you experienced it, and maybe can you throw more light on that?
Yeah, so actually checkpoints initially go into CPU memory.
Repeat.
Oh, sorry. Question about checkpointing and how we think about that as it like drives and how that scales out and where that might go in the future and the impact of checkpoints potentially on that drive capacity. So checkpoints actually initially go into CPU memory and not even to any durable media. There may be times where it'll be dual written, so it'll be written into memory as well as to the local NVMe on the GPU host associated with those GPUs. And the rationale there is that you want to have the ability to recover without going back to blob storage should you need to roll back to N-1 or one of the most recent checkpoints. Going into CPU memory allows us to flush those GPUs as fast as possible and get them rolling again. Because remember, the job is paused while those checkpoints are happening. And so because there's a correlation between GPU count and the amount of local resources they have, both in the form of CPU memory and disk, you kind of continue to scale that out. So the intent here is you're storing the most recent shards of the checkpoints locally on that NVMe, and then Blob might actually not capture every checkpoint. Maybe it's only every third or every fifth checkpoint that gets written durably back to Blob. When they go back to Blob, the idea is that these are more of a long-term retention. These are important checkpoints. These are ones that you can recover from should there be something that happened at the GPU host level. But typically the priority is to recover from the local checkpoints on the GPU hosts versus the ones sitting in Blob.
In your system, does storage always interact with the CPU, or do you see the GPUs actually directly interacting with storage?
The question is, do GPUs directly interact with storage, or is it always the CPUs? So Blob is a RESTful protocol. And the GPUs have a capability referred to as GPU direct storage, but that is really how does the GPU access the storage physically attached to the GPU host. And so that path is exercised for the checkpoints and for when reads or writes happening directly, and OpenAI does use that path. But when you're accessing blob storage, because that's all going over REST, that is fundamentally a CPU-based activity because the CPU has to coordinate all of that network traffic. Agreed. Thank you both.
Your wish list of things to get in terms of components or infrastructure, what's high to build the next better system?
What's the wish list of network of physical components for our infrastructure? On the storage side, we recognize the need to push the networking gear within our storage racks. We built our storage racks historically for much colder workloads, and so we do have an opportunity, and this is in a plan for upcoming generations of our hardware, to increase the throughput on a per storage node basis, as well as the switching equipment inside of our storage nodes. That'll allow us to just squeeze a little bit more throughput out of those hard drives. Did you have something to add?
I think there are a lot of things on the wish list, right? From as the drive sizes increase, what do we do about IOPS? How do we get more throughput from them? I think this whole audience has been talking about a lot of the problems. Those are the problems we see day in and day out, and we try to solve that through innovations in software and hardware to make it better.
In the Blob Views section, you talked about prefetching. Was that in the context of checkpoint restores or training data? Prefetching.
The question is about Blob Views and our future around what we can do with prefetching. I mean, there's a lot of reasons why you might want to prefetch. And the example that I cited was you've got training data that the GPUs need to process. And if you can send a hint to the client about which data in this exabyte scale namespace you are likely to be reading in the upcoming training epoch, you can get Blob Views to start reading that data before the GPUs request it. And so that's one prefetching scenario. You're right, though, there could be other scenarios where you're going to be switching a job run from Model A to Model B, and you want to, while Model A is still training, go ahead and start prefetching and warming up Model B's checkpoint so you're ready to go when you do the job switch, minimizing the idle GPU time. So there's a variety of reasons why prefetching can become valuable for these types of workloads. Other questions?
Are all storage accounts already scalable, or you have to set something up?
The question is, are all storage accounts scalable, or does something need to be configured? This is dynamically happening. So we monitor the heuristics of our public fleet. And so this is all Azure customers. This isn't specific to OpenAI. We identify accounts that are starting to bump up at some of these account level limits, either on the throughput dimension, the TPS limit, or even capacity. And then we're automatically doing the conversion to a scaled account behind the scenes. And like I said, this is actually a bunch of complementary technologies, and so there's a bunch more nuance behind how that works behind the scenes. But our goal here is to be able to remove limits from our customers across the fleet and not make this something they ever need to be aware of.
Yeah, because normally you have to manually hash out your storage account names, and so you avoid the repartition of why you have I/O. And is the Blob Views a continuation of the blob cache technology or something completely different?
So the question is Blob Views a continuation of the block cache technology or something different? Blob Views, if you're familiar with Views more broadly, Linux has a construct called file system and user space. And so what that enables is you can expose a kernel, or you can expose a user mode piece of code that interfaces with the Linux kernel that implements the standard I/O file system calls. And so what we've implemented is a open source package that works with libviews in the Linux kernel to take in those file system calls and then translate them to our storage as HTTP requests, as well as implement those sort of caching things. So Blob Views is an open source software package that Microsoft builds, maintains, and supports.
Yeah, because internally for compute, you have what you call blob cache for having write back for your premium disk. Which uses local NVMe and local RAM for some.
This is a different technology.
The question, there's some internal, to repeat the question, there's some internal capabilities that we do call blob cache, and it's for a variety of other capabilities internally. It's not something we really expose, and yeah, the answer is this has nothing to do with that. We just like to reuse names. That's kind of what Microsoft does. Any other questions? Oh, go ahead.
So is it Blob Views entirely open source or some parts of it?
Question is Blob Views open source? Yes, it's 100% open source, yeah. There's no private code there. Other questions? Awesome. Thank you all for taking the time, and appreciate the audience. Thank you.